Hey guys, I want to talk about a very specific type of motion problem that I call the meet-catch problems. These are very usual in Physics 1 and Physics tests, and I want to show you how this works. First, I'm going to start with a very simple example, and then I'm going to talk about it. So let's get started. Alright, so meet-catch, sometimes I might refer to these as chase problems. One animal's chasing the other, but one catches the other, right? So, very quick example here, 300-mile trip. So your trip has a length of 300 miles and your friends are ahead of you by 50 miles. You guessed that their speed is 55, so velocity of your friends is 55. It's average, so their acceleration is 0. And we want to know how fast you have to go so that you catch up to them. Okay, so what is the velocity that you have to have, average velocity, so that you catch up to them? In other words, so you arrive at the same time, which means that delta t of your friends is the same as delta t of you. And this is what's going to happen in these problems, these meet-catch problems. Your time will be the same as their time, or whatever two objects are moving. Okay, so if you want to draw this real quick, your friends are going from here. This is 50 miles. Your friends are going from here to here, right? This whole thing is 300, so this is 250. While you're going from here, the very beginning, all the way over here. So you're actually covering 300 miles. Okay? So you don't start from the same place. The time starts counting here, and the time ends counting here. Okay, but the idea is that it's the same time, so delta t equals delta t. It's the same times. All right, and the question is, how fast are you moving? So for this interval, they're moving at 55, and I want to know how fast are you moving. Okay, if you go straight for the answer, which is probably what you should do, you see that the average velocity equation is delta x over delta t. You know your delta x. Your delta x is 300. That's how much you're traveling. But we don't have the time. Right? So it's one of those where you're stuck, but there's another situation that is related to this one where you can find the time. The time for you is the same as the time for them. And I have enough information to figure out how long it takes for them to get there. So that's what we have to do. Okay? So I have to find this time here. So we're going to go to your friends and figure out what is their time. The only equation, again, is v equals delta x over delta t. So time, delta t, is delta x over v. Now, delta x is 250, not 300, and their velocity is 55. Let me talk about units real quick, because this is 250 miles, and this is 55 miles per hour. So these two cancel, and you have hours. Obviously, it's time. So it's going to be hours, and you have 4.55 hours. An important point to make here is that you don't have to convert anything. Everything's in miles or hours, and you want to know the answer in miles per hour, so you can just keep everything as it is. All these units are consistent. So I can just plug in that 4.55 hours here, and I get the answer, which is 65.9 miles per hour. You have to go faster than they are traveling, and that makes sense because you're trying to catch up. All right, so that's a very simple one that we could have solved without me even talking about this anymore, giving you any more details about this new type of problem. But let's get into that now, because we're going to have some more complicated stuff. So when two objects meet, the basic idea is that they are at the same place at the same time. And that's pretty obvious, but more specifically, this means that the x final of A is the same as x final of B, and the time of A is the same as time of B. Okay, they have the same time. All right, so how are we going to solve this? There are 4 steps. The first one is we're going to write their position equations. Write the position equation for each object. And the position equation, I will remind you, it's the third equation, but I'm going to draw it a little. I'm going to write it a little different. I'm going to say x equals x initial plus v initial t plus half of at squared. So it's this, except that I expanded the delta x into x minus x initial and moved the x initial to the other side. All right, so it's this one. That's the position equation. You write this for both objects. Then you set them equal to each other. You equate their position equations. This is the most important part of the instruction. Why? Because if you remember equate position equations, it's obvious that for you to set them equal to each other, you obviously have to write them first, right? So if you remember step 2, you're going to remember step 1. And if you remember step 2, you're going to remember step 3. When you set these two equations equal to each other, as I'll show you soon, the only variable you have left is time, and then the only thing left to do in that equation is to solve for time. So as long as you remember step 2, you should remember everything else. Once you solve for time, if you're looking for the distance at which they meet or one catches the other, all we have to do is plug time back into the position equations. Okay? So better than talking about this is to show this, so let me show you how this works. Alright, so a car starts from rest. So car has the initial velocity of 0 and moves with a constant 8 meters per second to the right. So the acceleration of the car is 8 meters per second. At the same time, a truck moving with a constant 30, so V average or V constant equals 30, which means the acceleration is 0, passes the car. Are they going to meet again? Yes, no. If not, why not? So do they meet again? The answer is yes. And it doesn't ask why do they meet again, but basically the acceleration of car is greater than the acceleration of truck. Right? This is 8. This is 0. So the car eventually catches up. So let me draw this real quick. This is the car moving with initial velocity of 0, acceleration of 8. And this is the truck. The truck was already moving, so the truck kind of comes from behind and then crosses over here. Alright, so the initial velocity of the truck, which is a constant velocity for the truck, is 30. The acceleration is 0. And the idea is that the time starts counting here. Okay, the time starts counting there because the car starts moving when the truck passes the car. So this is my x equals 0, and the time is 0 for both of these. Okay, so what we have to do is write the position equation. Remember, the position equation is x equals x initial plus VOT plus half of AT squared. This is the expanded position equation. This is your final velocity. So the final velocity of the car, the final position of the car is the initial position. They both start in the same place, so we call that 0. The initial velocity of the car is 0 as well, and the car does have acceleration of 8. I don't have time, right? And you should expect that you don't have time in these equations because you're trying to figure out when do they meet. So you're looking for that time and eventually you're going to get that. So as you're plugging these numbers in these specific types of problems, you're not going to have time, okay? So if you clean this up a little bit, it is 4t squared. I'm going to put a box around it because we're done here. Now x truck. The truck also starts at 0, but it has an initial velocity. It's a constant velocity, so it is 30t. Again, you don't have t, so you can just write 30t. And this truck has no acceleration, so this is 0. So you get 30t. That's the first step. You write the position equations. The second step is to set them equal to each other. So if I equate these two equations, I get 4t squared equals 30t. And the easiest way, the only way that I know to solve this is to cancel the t's, so I can solve for t. T equals 30 over 4, which is 7.5, and this is seconds because the acceleration was in meters per second square, the time was in meters per second square, SI units, so the time is just 7.5 seconds. So that's how you can do these problems. You equate their position equations. Once you do that, notice that the only variable is t. That's why I said that the third step up here is an obvious one. Is an obvious one once you've written their equations, right? So I got that time, and that answers when they meet. So they meet at 7.5 seconds. The next question is where do they meet? In other words, we're looking for x. Now I can plug this number into either one of these two equations right here, and that's because they're at the same place at the same time, right? So you can plug this into either one of them. So it says there you can plug that into either position equation, right? And I can, if you were to do this, you could see that for 7.5 t, that's x car, would give you 225, and or you could do x equals 30 times 7.5, and that also gives you 225. Okay, so that's your final answer for where they meet. So you're just going to plug it into the simplest one of your position equations. I want to answer the extra question there, which is to find the car's final speed. So for this, I can just use one of the motion equations, one of the three motion equations. I got them up here. The first one works. The final velocity of the car is the initial velocity of the car, which is 0 plus acceleration time. The car accelerates with 8, and it's been 7.5 seconds. So we do this and we get 60 meters per second. This is for the answer for the bonus question, and that's the final velocity of the car. Anyway, so that's basically how you're going to do these. You write their position equations, set them equal to each other to find your time, and then you're going to plug in that time back into either one of the position equations to figure out where they meet. And sometimes they're going to ask you how fast was one of the two objects, right? They're not going to ask you how fast the truck was going because the truck is a constant 30. But the car is changing its velocity, so it makes sense to ask for the car's velocity at the end. That's it for this one.